Okay, we are going into our next section, which is arguably one of the things that drove this theory freaking crazy in its development. This section has to deal with the radiation reaction. So we have a lot to say about this. Let's see what this is first by diving in with the question. So a particle of charge Q moves in a circle of radius r at a constant speed v. To sustain motion, you must, of course, provide a centripetal force mv squared over capital R. What is the additional force Fe you must exert in order to counteract the radiation reaction? Okay, it's easiest to express the answer in terms of the instantaneous velocity v. What power Pe does the extra force deliver? Compare Pe with the power radiated. Okay, part B. Repeat part A, but for a particle in simple harmonic motion with amplitude A and angular frequency. Hence, Wt is equal to A cosine omega t z hat. Explain the discrepancy. Okay, we might have a paradox come up out of this. Let's see. Now, consider, in part C, consider the case for a particle in free fall, constant acceleration g. We saw that just a couple questions ago. What is the power radiated? Comment on these results. Okay, so in addition to the Lamar formula, we also have the Abraham-Lorentz formula for the force radiation, the radiation reaction force. You see here we have the A dot in that position, which looks kind of weird that we need to consider the rate of change of acceleration. Let's go ahead and walk through this step by step and see what can be said about this. So A, to counteract the radiation reaction, you must exert a force Fe, which is equal to negative mu naught q squared 6 pi over c A dot. So for circular motion, okay, because again, if we want things in balance, the force has to be negative that of the radiation reaction force. Okay, so R of t moving in in circular motion, we have R for the radius, cosine omega t in the x hat, sine omega t in the y hat. Again, I'm lazy. I'm using angle brackets for the unit vectors, x hat, y hat. Take the derivative to get velocity. Take the derivative to get acceleration. What we see is that the acceleration is equal to the negative omega squared r. So then A dot is equal to negative omega squared r dot. But we know that r dot is just a velocity. So A dot is equal to the negative omega of v, omega squared of v. Similarly, just how A is equal to negative omega r. Much simpler to deal with. So if that's the case, what we see here is that Fe, if we plug in the negative, A dot, gives us mu naught q squared over 6 pi c omega squared v. Notice that the negative signs cancel. So if that's the case, the work done, which would give us the energy or power, is work done is F by F dotted with the displacement. So power being the rate of change is F dot the velocity. So if we do the Fe dotted with the velocity, what we see is that we get mu naught q squared over 6 pi omega squared v squared. Okay, and what this represents is this is the power you must apply. Meanwhile, the power radiated, you get it from the Lamar formula, is mu naught q squared a squared over 6 pi c, where a squared is just a dot a. If that's the case, what we have here is a dot a gives us negative r omega squared times 1, because the dot product of r and r hat is itself. So if that's the case, what we get is r squared times omega squared. But we know that r times omega is equal to v, so we write that as v squared omega squared. If we plug that in, we get power radiated is exactly the extra force that we applied. That's pretty cool. Okay. Now, if we move the motion to something else, like the simple harmonic motion, where we're given omega t, or not omega, but Wt is equal to A cosine omega t. Take the derivatives, of course. We see that V and A are such. A is equal to negative omega squared W. A dot is equal to negative omega squared W dot, which is equal to negative omega squared V. We saw that before. And so we see the reaction force, the additional force, and the power of the additional force. But here, omega squared v squared is equal to omega squared a squared sine squared omega t, versus the a squared that we had from the Lamar formula gives us omega to the fourth a squared cosine squared omega t. So the power radiated is not the same as the additional power. Okay, the power you deliver is not equal to the power radiated. However, since the time average of sine and cosine are equal to 1/2 over a full cycle, the energy radiated is the same as the energy input. Okay, so what we have to do is use the annoying unit, the annoying average power. So, yeah, be aware. It's not always what it's, this is the paradox here. We get a omega to the fourth instead of an omega squared, v squared. So, again, they had so many papers on this that I'll link below. But in the meantime, the energy delivered is being stored temporarily in the nearby fields. Okay? This is the thing you have to deal with these electromagnetic questions is the fields hold the answers. And this is what propagates things into quantum field theory and why we have such a visceral want to understand fields in general. So for the motion in part C, if it's in free fall, we just have R of t is equal to 1/2 gt squared y hat. If that's the case, we know what V and A are, and A dot equals 0, so the additional force equals 0. So the radiation reaction is 0, and hence the power is 0. But there is radiation according to the Lamar formula. Evidently, energy is being continuously extracted from the nearby fields. This paradox persists even in the exact solution where we don't assume that V is much less than C, as in the Lamar and Abraham-Lorentz formulas. So, yeah, this the concept of the field doing or holding everything is going to continue as we move on into our next chapter 2. So what we learned in chapter 8 is now being applied once again in chapter 11. It's not leaving us.